I'm Dr. Roger, and today we're looking at systems of first-order linear ordinary differential equations with constant coefficients, and I'm particularly interested in sketching the phase portrait of our solution once we reach that point. In this case, we'll have two negative eigenvalues. Let's solve for those eigenvalues, and we do that by setting determinant of matrix A minus lambda times the identity equal to 0. So that is negative 5 fourths, 3 fourths, 3 fourths, negative 5 fourths, minus lambda times the identity. So I'm going to write 1, 0, 0, 1 for the identity, which gives us negative 5 fourths minus lambda, 3 fourths, 3 fourths, negative 5 fourths minus lambda. Determinant, that's not really equal anymore. That's the matrix I want to take the determinant of, and the determinant is this product minus that product, AD minus BC. So that would be lambda squared plus 5 halves lambda plus 25 over 16 minus 9 over 16 is plus 16 over 16 plus 1, and that determinant equals 0. This factors and that product equals 0, so either the first factor is 0, lambda 1 equals negative 1 half, or the second factor is 0, lambda 2 equals negative 2. Taking the first one and setting matrix A minus lambda times lambda 1 times the identity times vector C equals the 0 vector will allow us to solve for the eigenvector that corresponds with this eigenvalue. I'm going to call that eigenvector 1. So A minus lambda I is negative 5 fourths minus negative 2 fourths is negative 3 fourths. Times C1, C2 equals the 0 vector. And this gives us the equation negative 3 fourths C1 plus 3 fourths C2 equals 0, which of course tells us that C1 equals C2. So if I choose C1 equals 1, then C2 is also 1, and eigenvector 1 is the vector 1, 1. If I do the same thing for A minus lambda 2I, eigenvector 2 equals the 0 vector. For lambda 2 equals negative 2, negative 5 fourths minus negative 2 is positive 3 fourths. Times C1, C2 equals the 0 vector, and if we choose C1 equal 1, then C2 equals negative 1, and our eigenvector is 1, negative 1. In some applications, eigenvectors are required to have magnitude 1, so you would take the sum of the squares of the components, square root that sum, you end up with 1 over root 2 and negative 1 over root 2. But in most applications, we're fine, and it's easier to use nice, pretty numbers like plus or minus 1. So our solutions are the form x equals e to the lambda t times the eigenvector. So our first solution is e to the negative 1 half t times 1, 1, and our second solution is e to the negative 2t times 1, negative 1. Our general solution for a system of two first-order linear is x equals c1 x1 plus c2 x2. So x equals c1 e to the negative 1/2 t 1, 1, that's my x1 solution, plus c2 e to the negative 2t 1, negative 1, where x vector refers to coordinates x1, x2, or I could make it xy, but I'm going with x1, x2. Our phase portrait, which geometrically shows the behavior of our solutions over time in the x1, x2 plane. We have eigenvector 1 in the direction 1, 1, so that's a line with slope positive 1 for the origin. And the eigenvalue is negative, which I'll indicate with arrows moving inward. If we start at a point on this eigenvector, as t increases, e to the negative 1/2 t decreases, we move toward the origin as t increases. Eigenvector 2, the direction 1, negative 1, is a line with a slope of negative 1 for the origin. 1, negative 1 means we move right 1 in the x1 direction and then down 1 in the negative x2 direction. And this is eigenvector 2. And the eigenvalue is negative, so we're moving in along this one also. Since the magnitude of this eigenvalue is greater than the magnitude of the first eigenvalue, I'll indicate that inward arrows because we're moving inward, but I'll do a double arrow to visually remind myself that we move inward faster in this direction than we do in the other direction. As t increases, both components go to 0, but this goes to 0 faster. You can think of this as meaning our initial position in the direction of eigenvector 2 goes to 0 faster, so we move toward eigenvector 1 and then along it toward the origin. Eigenvector 1, that component is also decreasing, so we're also moving inward, so it curves inward to the origin, and our solutions will look something like this over time. Where both components are decreasing, and it is important and helpful to label all the trajectories with arrows pointing, in this case, toward the origin, because that's the direction of your motion along that path. It's not a perfect sketch, but it's a reasonably good geometric depiction of your behavior in the x1, x2 plane, and this can help you build some intuition for the behavior of the system. It's important to be able to sketch these trajectories and understand them intuitively. You can also graph them on your calculator in parametric mode. So the steps: determinant of a minus lambda times the identity equals 0. Calculate that determinant, solve for lambda, and then for each lambda, a minus lambda I times your eigenvector equals the 0 vector, and find the eigenvectors that correspond, and your solutions are e to the lambda t times the corresponding eigenvector. Come back soon for my next video. With math, there's always more.